known to solve for sleep. So first, let me give you some observations. So let's consider maximally symmetric ODEs. I will use jet notations. So here, yes, there's this equation that's symmetry. Okay, so see here is SL3. Here it is SP4. And here it is GL2 semi-direct S n minus 1. I will walk over C. So it doesn't matter in these computations, but it does matter later when classification. That's very simple. If we consider equation of order n, which means that derivative by n's jet is non-trivial, not identically 0, it means then the symmetry algebra is finite dimensional, and that's where the maximal symmetry algebra is attained. There's unique such equation. Up to what? Here, point, and everything from this moment contact.
So maximality in dimension.
Maximality in dimension, yes. So when we talk about maximal dimensions, then it's actually just one up to the corresponding. So at this point, actually, we have to consider point because up to contact, everything is the same. But from this moment, it's actually reasonable to say contact. So what about this group? So that's actually point transformation group, right? It's actually maximal among infinite dimensional. This one is also maximal in contact group. This one, it's not actually contact. Well, of course, we can say contact. Женя, Maxim, привет. But this is actually essentially point and even fiber preserving. Okay, so when we talk about the splitting, right, that's foliation. So transformation actually are lifted from J0, right? Sorry. That's simple observation because that's a very explicit algebras, right? Essentially fiber preserving. Well, point fiber preserving. This. Yes. Right. So that's like okay. So that's one observation, right? Well, that's very simple group, right? So that's actually a couple of scalings here, and well, just del x, x del x, x squared del x there, right? Which makes us to in another scaling. This one is really contact. Whatever change of variables you do, it cannot be point. So that's essentially contact, and that's essentially point. So you cannot really make it smaller. This is really not fiber preserving. It doesn't preserve any foliation. Yeah, and this is contact irreducible, cannot be reduced to point. Okay, so that's first observation about maximally symmetric. Okay, so let me give the and already this kind of give a question like, I mean, why is this so questions which have so many symmetries actually? Well, we talk usually about contact symmetries for equations, but there's not that many that have actually contact symmetries, right? So, okay, so let me give another example. Just this equation. So actually, like these equations do possess contact symmetries. So like this one don't, right? So they actually essentially point even fire preserving, right? Lift of those. But these do actually preserve essentially contact symmetries. This one has 3 and this one has 1. Okay, let me here remove essentially. However, if you do Legendre transform to this, then for the first equation, we will get just this. And for the second equation, we will get just what? This. So first equation, second equation is not linearizable, and that's because we can look at the symmetry algebra, and it doesn't contain any three-dimensional abelian subalgebra. But then basically the result is the same. So that if we slightly adjust, then actually they become all point fiber preserving. Okay, and submaximally symmetric these are such that the symmetry dimension drops by 2 actually. Okay, so the symmetry dimension you can read off from here, right? 8, 10, n plus 4, right? So and these are just reduced by 2. There's a small gap. So minus 1 is not realizable as symmetry dimension, but minus 2 is realizable, except for n equal to 5 and 7, where there's no gap at all. So 5 and 7 are a bit special. So let me just write what happens actually. Like, and for all of them, the symmetries are essentially, well, just fiber preserving. Except for, and there's 3 exceptions. Okay, and let me write those exceptions. These are kind of funny equations, so let me write those. So that's fourth order equation, easy to integrate. And the symmetry.
One is also submaximal.
That's not actually, that's minus 2. Yes, that's submaximal. That's true. That belongs to submaximal, but that's not exception here. That's dimension minus 2. So that's affine 2, right? So that's dimension 6, right? And for 4, this thing is 8 minus 2 is 6. Okay. So this is point, but it is well, not fiber preserving. And then there is L5. Okay, and this is SL3. Dimension 8. So it's again point, but again, not fiber preserving. That's quite known equation. It's Klein equation. Its solutions are all quadrics on the plane, right? And there's also fun equation which is this. Okay, so it's a bit long, but it's actually also a very funny equation because, like, for those two equations, the gap is just one. So that's two exceptions. This equation is related to more complex, but also to nice algebraic curves. There was a paper by Dunajski Sokolov about it, somewhat like 15 years ago, maybe. So for it, the group is SP4, and that's just contact, right? Well, yeah, group algebras, of course, yes, algebras, yes, because, yeah, algebras. Okay, so so just like these are like maybe like most interesting equations, and for all of them we kind of observe fiber preserving property, and that's strange story, right? So basically, in studying symmetries of differential equations, maybe up to some conjugations, we don't see contact transformations or even actually point transformations. And the kind of strange message is that majority of equations which possess symmetries possess only fiber preserving symmetries.
Just a small question. And how these results were obtained? By direct computations or some technique?
You mean this or those? No, this is of course direct computation. Yes, you just load it to Maple and
general ones.
Of course, you do splitting. You write the equation, you split it, get over to systems, show to PDSolve, and you get it. And of course, you also have to see you get 10 symmetries, but you have to see that as SP4C. But there's well, actually, for example, this one. Of course, the interesting story how this is obtained, for example, right? How is n+4 obtained? Because when you get n+4, it's not difficult to see. These things are just shift by solution because it's linear equation. That's easy story, right? You shift by any polynomial of degree up to n-1, right? And this one is easy to see SL2 acting in there. So you just see those symmetries, they're independent and you can't get more than this. How we get bound, actually, even the interesting question, how you bound away from infinity. Olver, in his book, Symmetries, Equivalence, and so forth, he actually discussed this, and he discussed this and drop by 2. It actually goes back to a certain extent to Sophos Lee. What is not actually is there. It's not like the proof that the maximal symmetry, well, so that it's affine dimensional is not in there. Afterwards, actually, just look to classification of Sophos Lee of all Lie algebras of vector fields. You compute differential invariance, and you can see actually what is the smallest differential invariant, and this gives you this. That's kind of Olver's approach to this. We have different approach to this. So you first, like in Olver's books, actually, there is proof that symmetry dimension is fine dimensional based on old work of Sokolov. And that's something you write for this. It's equation of total derivatives, and equation of total derivatives is overdetermined system, and then you kind of look to this. Our approach to this is quite different. You write the corresponding distribution. There is Tanaka algebra associated to it. You compute its prolongation. It's fine dimensional. That's the bound. That's completely algebraic proof. Okay.
What about -2 and -1? Я у вас кресло для Алексея Брониславовича.
Давайте мы заберем его, да. Давайте я перевешусь куда-нибудь.
Сюда.
Или сюда. Угу. Actually, this one is also written in Oliver, but the proof is also ad hoc. You go through entire Sophus-Lee classification of algebras, and you just look what can happen there. I mean, more conceptual, more not case-by-case proof was recently given by Dennis Ste with his PhD student. Just Lie algebras on of vector fields on the plane, right? That's point, and then also contact. Everything like contact vector fields and also there's complete classification. So yes, in 3 dimensions, yes. Yeah, that's complete. Okay. So kind of message, I don't really want to make it into theorem, but message is the following. So there are actually equations for which there are essentially point and essentially contact symmetries, but there are very few. Like they are meager in this space of all equations. We can make it into kind of mathematical statement, but we have to do some setup. For example, we consider algebraic equations. The left-hand side is polynomial or quasi-polynomial, and inside of those, it will be like subvariety, definitely of stratified subvariety of small. So that's actually, if you think about algebraic side of this, you consider all algebraic equations. Among those, you consider some ODEs with infinitesimal symmetries. And among those here, you consider those with essentially contact, for example, transformations. And this is a mega set inside of here, but this is actually quite a complicated set if you think about this, even if you start just with algebraic equation. You can, of course, restrict order. You can, of course, to do some filtration of this. You also can restrict degree, polynomial degree, but it's still like even the smallest, in simplest examples we computed, it's algebraically pretty complicated. But that statement is completely true. Like, but you can also apply to other classes of equations. So that's mega set. Small in all senses, right? So like countable union of nowhere dense or whatever. So it's possible to do, but we actually, the point of doing this was different. So can we actually classify all equations which allow essentially contact symmetries? Or among those which do point, all of those which allows essentially point, which means not conjugated to Fourier preserving. Okay, so and yes, and that's not very difficult. So let me just talk about this part. Yes, so that's nothing. No, well, no, it becomes pretty wild afterwards. Becomes pretty wild, yes. So even to obtain all those submaximal, not just examples, but all of those, it's kind of complicated. This was done recently by Dennis Ste.
These indices mean derivatives.
So no, there's the dimension. There's dimension. There's dimension. Dimension of symmetry algebra.
So what does Y2 mean?
Submaximal.
What does Y2 mean?
Dimension minus 2.
But Y2, what does Y2 mean?
Ah, yes, sorry, it's just jet notations. Yes, second derivative.
So
Yeah.
our last question is this looks like a kind of a fake degree 5 because it's really degree 3 in Y2. Why do you consider? I mean, this seems to be the case for all of them.
You mean that you can reduce order?
Well, I mean, there's this stupid thing.
You can integrate this. You can integrate this equation. You can integrate this equation, but reducing order is not correct way to integrate it. Actually, if you reduce it, you will not integrate it. If you would like to integrate it, that's actually all solutions are quadrics. So the number of quadrics on the plane is 5-dimensional. So actually, yeah. So that's all solutions. If you reduce the order, right, by substituting y2 equal to w, you will not see it.
Could you say me third term in this L7 minus 49? Could you please pronounce?
Yeah, let me just recheck. Maybe I did wrong. You know,
Y2P and
I think it's actually, yes, you're right, Maxim. Yes. Yes, because of course there's also some scaling symmetries which you can just recheck. Very good. Okay. So so let me then tell you what I'm going to do. So for example, task 1. Well, classify all ODEs with essentially, let's say, contact symmetry. That's a bit ambitious, so let me change this to list. And I'll explain that actually classify will be way too difficult, but list is actually easy. So list means I do something with repetitions. I don't want to bring to normal forms, right? Okay, so how am I going to do it? I'm going to do this through computing differential invariants of certain Lie algebras. The algebra G of contact vector fields is called irreducible if there doesn't exist a Legendrian subdistribution. Actually, yes, invariant. Actually, let me just remove this. Of course, invariant it's always needed, but I would like to talk about the case we're discussing. So we're discussing J1 of map from one-dimensional to one-dimensional. I walk over C, so that's three-dimensional manifold, right? So contact distribution here is just 2, rank 2, and so what it claims there doesn't exist a line subdistribution, invariant line subdistribution, right? That's irreducible. In Cartan, yes, yes, in contact plane, yes. So otherwise it's called reducible. If such thing exists, then we can always make it vertical by contact transformation, and then all distributions are actually project to points, so they're prolongations of points. That's precisely, that tells what is needed. Now, so yes, local on base, global on fiber, as you. I mean, it will be transitive on base. I'll make remarks a bit later about this transitivity, how things change if you do something on the base. But in fibers, it's global story. Okay. I will be using Sophos-Lie classification. It's local classification, local analytic. Yes. So in 3 dimensions. So that's obviously classified, well, everything in particular, well, in low dimensions, particular those irreducible algebras, and there are actually 3 of them. So the biggest one is SP4, we already saw it. And then there is parabolic subalgebra in here, which abstractly is isomorphic to GL2 semi-direct C, no, semi-direct, what? Heisenberg 3. Heisenberg 3. It's C2 semi-direct C, right? But then this semi-direct doesn't communicate with the semi-direct. Okay, so that's first parabolic. If yeah, I may recall it later. it's like on the level of the linking diagram, that's CP2, and then we cross out this node. And then there is subalgebra in here, another maximal subalgebra. Well, that's 10-dimensional, that's 7-dimensional, this is 6-dimensional, just SL2 semi-direct Heisenberg.
Just a question, what do you mean by 3-dimensional case?
This.
The basis.
Yes, the J1 is 3-dimensional.
J1, not.
It's just ordinary, right? So it's X here and Y here. Just 1-dimensional here and 1-dimensional there. Okay, now if you'd like to, actually we would like to compute differential invariance for all of those, but there's no need, because if something is invariant with respect to big one, it's also invariant with respect to small one. So we'll just do computing differential invariance for this guy. Okay, so we will restrict to this story. Okay, so let me give you this algebra explicitly. It's contact, right? So I can't write point. It will actually contact algebra. I don't write y0, right? I will just write y. Okay, so that's this guy. Well, you can probably see SL2 somewhere. It's probably this one and this one. No, it is SL2. Actually,
The third and the fourth. No. Sorry.
huh?
No. Where dx, x dx, and x squared dx.
There's no x squared. No, there's no x squared dx. You might think about this one, but it's not. Sorry, I forgot. But it's somewhere here. It's my bad. I forgot. Anyway, that's correct thing. So now I will enumerate this vector field with S capital. In particular, for example, this one will be X capital 5, and this one will be X capital 6, and so forth. So I would like to remember the scaling transformation in particular from this algebra. So I'll be talking about differential invariance for this algebra. So what we are going to do, we are going to compute xi prolongation j, and we are going to look to invariance. The infinitesimal approach would be to do this, right? So where I is some functions on jets. And jets are, well, those J1 from C to C.
So the prolongations in GDEq you can take invariant.
Yeah, maybe, well, here I don't take infinite, right? Here I take prolongation just to J, but can do to infinite, yes. But let's actually be a bit more careful here with definition. That's not good definition of differential invariant. I'd like to talk about actually algebras. I don't want to talk about Lie groups, in particular because these algebras I consider in some affine chart. This thing is just affine chart. For example, if I would like to integrate this group or this algebra to a group, some vector fields will be incomplete in this affine chart. I will not get group, but I can actually get a good pseudo group, 10-dimensional pseudo group. If I integrate this to group, the group will be just what? 7-dimensional, not 10-dimensional, right? So because some vector fields will be incomplete. But that's not a problem. I can work with pseudo group. Pseudo group will be nice, also locally 10-dimensional. So, and of course, the correct way to do it is to take any of these Lie algebras and integrate to pseudo group, and then state that with respect to pseudo group, this thing is invariant. There's still alternative way we can work with algebras, and how we do it, we can say that, well, of course, vector fields are lifted, and the section of Lie algebra on corresponding jet space, and they're orbits. So I shall be constant on orbits. It's not quite the same as this. There's an example in my paper with Valentin where actually it's quite tricky. So that's strange story, but just like even though group can be connected, right? So but it's not the same as Lie derivative equal to 0 and or invariance with respect to corresponding pseudo group. Okay, so that's about invariance. So differential invariance is something which is constant on orbits. Orbits we can talk just from the algebra. Don't need to do integration. And I also will need relative invariance. So this thing is absolute invariant. Yes, it will be everything as actually in setup of Valentin's paper together with me, which is called global Lie tracer theorem. And the setup is there. So this all actually Lie algebras are algebraic. If you integrate to pseudo groups, they will be algebraic. And therefore, we know that the generating set of, by our theorem, the generating set of absolute invariance is rational in higher jets. So we use this. We don't actually require that the equations we want to get afterwards need to be actually algebraic. We may want them to be, for example, analytic, but generators will be algebraic, right? So we can take analytic combinations of algebraic generators. So this solves all problems. If you would like to get a list of all algebraic equations, we'll get it. Analytic equations, we get it. And that's a kind of a bit advanced to what Sophus Lie did actually, because like, of course, Sophus Lie did everything absolutely locally, but we are not super happy with doing locally. So let me show you one thing, like which just, if you're not fluid in differential invariance, fluent in differential invariance, so maybe it will be helpful. Kind of small example, just reminder about differential invariance. So let's consider the following actions. The group will be, I'll do real story here because I'd like to draw. The group will be R cross and will act, here's element T, and will act from R2 to itself, namely point xy is going to Tx T minus 1y, right? So that's absolutely trivial dynamical system. We know the trajectories, here they are, right? Now, what would be local approach? Local approach would be the following. We say, okay, let's just localize to some part of the orbits. You concentrate on this part, right? And then you see, okay, here's trajectories. And of course, what will give you invariant? Everything which is transversal to here gives you invariant. And what, for example, y? Yes, this function here, y. That would be an invariant, right, from this viewpoint, but it's not, of course. So you can, I mean, so you take this y, right, and you would like to produce from it an invariant, and so actually you for x equal to 1, right, and then you expand it along the floor, right, and then you see I equal to x, y is an invariant. And that's actually fine, right? It's real invariant, and but it's a bit more here story. So here you see that this invariant completely separate all orbits. right? Because, well, precisely the value gives you one orbit. And that's almost true, right? It's true, it's separate this orbit, but there's one special thing, you don't see it. There's this one. It doesn't separate because it gives you this, but it's not separable. So you see this thing, right? And you see also this thing. For all of those pieces, the value of I is 0. But these two union and this two union are different orbits. So it doesn't separate, right? So if you would like to do global story, then you have to be a bit more careful. So that's the point of this example. Well, I mean, yes, we discussed with him many times, of course, yes. So one have to be always a bit careful. That's a very simple example, which shows what happens, right? But you just don't see even singular orbits with this thing, and there are more complicated examples where such thing happens. So even though it's like true that like locally it was done by Sophusly and so forth, but it's slightly, well, you have to take a bit of care. Okay, so one more thing. I will leave this for a moment. Also, let me recall your relative invariant. So what is relative invariant? So relative invariant is also a function on jets such that R equal to 0 is invariant submanifold. Well, since it's functional jets, it's differential polynomial, so that's actual differential equation, that's invariant differential equation. And in analytic terms, right, you do very similar story in here. Let me actually really don't take care about order, but just write like this. Of R. So now it's not 0, right, but proportional to R. Who is this lambda? So lambda depends on X, right? So lambda is actually belong to this. So here you put your X, that's dual algebra, and here you get function. So that's actually function on jets, right? Now, in fact, if you write this equation, because of course you have to do commutation for different x's, let me just write it like this: X belongs to G. Then you see that this lambda is cocycle mod coboundaries. So cocycle is just get this condition because, well, one cocycle, because because you do computation of Lie derivatives and then you get the equation of cocycle, and coboundaries happens if you change R, right? Because R equal to 0 defined invariant thing, but you of course can define it by multiplying R by something else. It will define the same thing if you multiply by something non-zero. Then lambda will be changed precisely. Then it's a bit more complicated. At this moment, I talk about analytic. If you talk about analytic, this gives for us precisely H1, H functions on jets, right? This is a coefficient. This is the algebra that's represented in here through vector fields, and then we get this. If you talk about algebraic situation, it's a bit more careful, bit more tricky. There's more coboundary is not completely true, but I'd like to omit this point.
And is the smooth case different from analytic?
Not really at this point, of course. There's no big trouble. But I mean, when no, this is of course the same. Yes, it's just continued cohomology. If you want to Kilfan-Fuchs cohomology, you can say. But it will be different in classification, right? So this classification of algebras of vector fields is actually fine for analytic, but for smooth there can be. Okay, over real classification is much longer. Yes, over real it will be much longer. So everything is over C. That's why it's analytic. Yeah. Okay, so that's I mean, and now comes actually a bit of specification, right? Because we would like to do algebraic. So this for absolute is going to be actually rational functions. for relative invariance, we really want just polynomials.
This is another result.
Nope, nope. It's actually a statement. It's a theorem. Yes, and you can actually expect, well, that's actually a theorem which belongs to Valentin and me. That we can always do it. That's this one.
Yes, yes.
And this one, well, in a sense, it kind of follows. If you have like rational, you just think just in this, you clear denominator from one point of view. More complicated stories that you can actually do this also for cocycle. Yeah, then it's really constrained. So that's a lot of already polynomial story in here. But if you don't restrict, then actually this equation is not that interesting. It's not that rigid. So, okay, so let me show you how to compute this relative invariance for this particular case. Okay, so I'll just write the first relative invariance. Something similar, but not completely the same what was written before. Sorry. Oh my God. That's R6 first of all. I have to write R5 first. Yeah. For this one. It's one dimensional. No. Actually, I'm not sure. I mean, because actually that's not everything here, right? So that not every cocycle give relative invariant in principle. So I would say that there's, I know effective part of it. Let me write one more. It's actually infinite sequence. Okay, so let me just write first relative invariants are like this. Yes. Yes, it just in a moment. So this one is kind of clear, right? Because well, I wrote here 3 algebras. This was the smallest, but biggest was SP4, and SP4 is just symmetry algebra of this, right? So that's clear. But the others are a bit special. So there are some similar to what we had before, but not completely. So actually, maybe I'll write the relation to what was written before. So this R5 is L4 of Y1. So we had this polynomial L4, and we substitute there not Y, but Y1. Raise the order, we get this. So very similar R6 is L5 of Y1. So this is this Klein ODE, right? So Klein nonlinear operator. And this is raising the order. There's some explanation why we have to raise the order. there's relation, there's some reduction of contact to point, non-trivial one for those algebra. There's also a relation of R7 to L7, but I'll just not write it. We posted archive preprint with Eivind Schneider, my co-author, yesterday, so it's available in archive. But I don't have number, but it's a recent archive. So now, in this case, for this algebra G, right? So what about those guys? So I say relatives. There's some lambda, right? So lambda, well, actually, of course, it takes place in some linear space, right? But there, it's actually discrete. So it's lattice there, or even not lattice, but additive subset of lattice. So in all those examples, actually,
When you mean lattice, what do you mean when you say first?
well, lattice is, yeah, discrete subgroup. Yeah. Just a moment. So what about this cos cycle? This cos cycle actually is this. For this case. Sorry, too many x's. This is capital. That's vector field. And the other one is coordinate on the base. So horizontal differential, right? That's one. Well, it's space of horizontal differentials here is just one dimensional, right? So therefore they are proportional. That's why I divide. That's how a cocycle is obtained. Actually, all cocycles are obtained through some differential forms. There's no theorems like this. It is observations. So either contact to some volume forms or whatever, some divergence. I don't have any abstract theorem for this, but every time I can find something, some expression of this kind. This can be more complicated. Okay, so in fact, note the following. So lambda of x5 for this vector field is actually 1. And this vector field, if it's infinitely prolonged, let me erase now the story. This vector field, let me write infinite prolongation of it. So
From 1 or from 0?
It doesn't matter, right? It's n. So therefore, a relative invariant has weight W lambda, where lambda is this. And it's actually lattice, so it will be proportional to lambda. It's one-dimensional lattice. Yeah, it's just a weight, right? It's actually integer number. It's natural number, but to remember weight, yeah, usually we use all letters n, m, k. So that's integer. So W is natural. Lambda is this. Lambda is this basic weight, and all other weights are proportional to this. And since it's one-dimensional, we just forget about lambda. We'll identify it with natural number, the weight with natural number. And what is this? If every monomial has W differentiations by x. So here it is. This is 3. This 3 plus 5 is 8. This 4 plus 4 is 8, right? There's 3 plus 3 plus 6, 12. 12, 12, right? So here's weights. 3. Oh, that's awful. Okay, 3, 8, 12, 16, 20, 24, and so forth. For those that I didn't write. Okay, so this one is kind of exceptional, right? You can see that this goes nice arithmetic progression, the others don't. Okay, so so how we actually get them? So in fact, let me erase something. I think it's good to erase the central part. Yeah, I'm going to write it. I maybe still leave the algebra.
We have one new variant.
It appears like this, but let me wait a bit. So before I actually go to so before I finish the story with relatives, let me actually tell you a story about absolute theorem. So algebra of absolute invariant is generated by I5, which is R5 cube divided by I R3 power 8. Absolute invariant is relative invariant of weight 0, right? So this is relative invariant of weight 8 times 3, and this is relative invariant of weight 3 times 8. Difference is weight 0, right? So it's absolute invariant. But that's smallest. The first relative invariant appears in fifth jets. Yes, that's the first absolute invariant. And invariant derivation. How does it work? That's total dx, right? Okay, so that's complete description. So we have I5, then we have nabla I5, then we have nabla square I5, and so forth. Really, it's one in each order. There's order 5, order 6, order 7, and it's just one. But it's very simple story here, right? Because we talk about what? We talk about this. Right, it's just one dimension in each order. So that's really simple story here. Yes, so if you would like to get arbitrary differential invariant, you take arbitrary function of those. If you would like it to be algebraic, it's algebraic function. If you would like it to be analytic, it's analytic function. And that's global statement. That's rigid algebraic statement, okay? So now let's go to relative. So for relative, I actually do the following trick. So I'd like to, in order to be able to produce this list, I'd like to have a relative invariant derivation. So how do I proceed? So I do the following. I take nabla of some relative invariant, but of course, relative invariant will be relative invariant if I multiply by any function. So definitely it has no sense if I differentiate it. So what I first do, I make it I produce from it. So let this be of weight W. Just let's R be arbitrary relative invariant of weight W. So what I do first, I do this. I produce absolute invariant from it, right? And then I also multiply a bit more. Okay, and this is called nabla W of R. And it's what? It maps relative invariance of weight W to relative invariance of weight W plus 4. And that's polynomial. Even though there are some divisions, that's polynomial. Okay, so let me actually write it then in polynomial terms. Okay, so there's another theorem here. Yes.
And this is derivation, the lift of this is derivation in the
when we no, even when we apply it to absolute invariant, it's 0. This is not 0, right? So it's relative.
No, I mean, if you multiply, it's lift of derivation, so it's all in invariance, absolute invariance, it takes like your previous number. Just claim that if you put here tau equal, you get
it's related by multiplying by some relative invariant. Yes, of course. If you put here W equal to 0, there's no this thing, right? It's like nabla applied to absolute invariant, but there will be still factor.
For me, it's much more transparent if you talk about absolute invariance and this module over there.
Yeah, but it's a bit actually difficult to do it because actually to be rigorous, it's field actually, right? Because it's rational invariance. We know it's possible to do it to the bit finance here and make it into algebra because we can say it's field up to certain jet order, and from this jet order it's polynomials, right? Rational up to certain order, polynomials from some. Possible to do it in algebra, but this will be completely polynomials. That's really algebra. So algebra of relative invariance, okay, is generated with respect to G. Let me write what's nabla W. Nabla W is actually pretty simple. And maybe this answers your question. When nabla is actually derivation, this is first order operator. You see, it's on. Yeah. This is the same. I just demonstrated this polynomial, right? That's the same formula, but there's no denominator actually. Everything cancels. No, but this theorem is much more tricky. As it's written, it's wrong. If you would like to think about algebra generation, as usual, people talk about algebra, right? And that's always very complicated if you think like about Hilbert problem for generation of algebra of invariants and so forth. So it's actually, unfortunately, not true. It's actually true in the following sense. So what's the sense here? The sense here it's actually that we take I5, we take nabla I5 and infinitely many other nablas, and we take finite number of those and functions of those, right? Algebraic or analytic depending on setup. So here it's almost the same. We do this, right? We take relative invariance. Now, when we do functions for relative invariance, we have to take homogeneous combination, because when we talk about the algebra of relative invariance, that's graded algebra, right? That's not algebra, it's graded algebra. So RW1 times RW2 is inside RW1 plus W2, right? But we cannot sum two different things. So element is homogeneous, right? We don't sum in homogeneous elements. So sum of two relative invariants with different weights is not a relative invariant at all, right? Yes, so that's graded algebra, right? So that's important to remember here. So what we do here, we do this combination of homogeneous polynomials of those, but then sometimes we have to divide by R3. So there's localization involved in here. Plus localization by R3. So we have to allow the division by R3. That's the only thing. So there can be polynomials which we obtain, and they can be reducible. R3 appears if, and yeah, and
And what happens if I change algebra for
unfortunately, it doesn't make maybe big sense for relative invariance, right? So it's yeah. Yeah, but I may allow to filter with this R3 in denominator only. It will work. Then it's easy generation, but it's still something different. So let me give you an example, actually, why it is important. Okay. So actually, I took a lot of time for this introduction because this part of kind of was known to so forth, namely previous theorem, which I wrote here. I don't know, field or certain algebra of absolute differential invariant is generated by I5 and nabla, right? So if you take it in this form, if you remove this word field and just say all differential invariant is generated by this, that's obviously for sure. And that's contained in the book of Older, right? You have to specify what you mean by this integral field, like this precise algebraic sense. Maybe that's not so fussy, but okay, that's kind of bit specifying of so fussy. So this maybe was not in the this relative story, but what is really important that this generation, of course, is kind of new effect. We didn't know about this. So let me show how it works. So how do we use these in order to list all equations? Okay, so let's list all invariant ODEs of order 5. What do we have? We have just R3 and R5. We can only do combinations of those, right? So what do we do? CST, that's coefficient, and then R3 power S, R5 power T, and then 3S plus 8T is equal to W. That's R. That's homogeneous element of weight W. And these are just arbitrary constants, right? So that's just general story. Now, what is this? We can, of course, take R3 away, divide by it. That's what I say localizing. Then we get polynomial with one variable. We factorize it. Polynomial with one variable. It's principal ideal domain, factorize, so we get decomposition into factors. So we get just R3, R5, and this combination, R5 power 3 minus C R3 power 8. Right, so we always can factorize this into factor of this kind. This is clear, this is clear. This one by rescale, well, if C is 0, of course, it's one of those above. This can be by change of X, by rescaling of something can be made into 1. So it's just 3. So of order 5, there's only 3 essentially contact ODEs. Right, so if ODEs, for example, has order 4, explicit order 4, then its symmetry algebra is not contact. By conjugation, it can be made into point. Right, because it's only 3 here, but it's just because it's PAD. Okay, so let's increase the order.
When you speak about essentially algebras, so this means you can't bring it to point form by contact transformation.
Yes.
Right? But
No, you cannot. Yeah.
Yeah, but can you say bring it to the form only one generator is contact and the other contact? This least number of generators that can leave contact.
Yeah, I think it's possible, but that's a difficult question. Basically, you look to algebra, right? And you look to all subalgebras, and then you ask this question for each subalgebra, right? So whether you have subalgebra of codimension 1, which is point, right? It's answerable, right? But it becomes difficult because you're going to branch a lot in this question. That's not easy answerable question. I think I just removed the story. So let's step one step above. So let's do the same up to weight. What was 5, 6? Okay. So now R will be sum CRST R3 R5 R6 RST 3R plus 8S plus 12T equal to W, right? So similar story. And again, we can take away R3, but now it will be polynomial with 2 variables. And there's no PID theorem, right? There's lots of irreducibles here. And that's already difficult classifiable problem, right? We can do something about low degree, but right away, even for polynomial with 2 variables, we get into trouble. So these things show the difference between actually what I wrote there, classify and list. It's easy to list, but difficult to classify because here I just see what's going on. I just rescale this and make it to 1. That's 3 normal forms. But doing here, it's very complicated, right? Because I'm going to actually classify all varieties inside. It's a question about curves. Actually, it's doable, right? Curves in P2, that's doable, but the next one will be undoable, right? Now, I would like to do a particular combination for this one. Yes. So a particular combination of this is the following. Right, so that's of this kind, right? And it's reducible. So I will not write what R6 is. It's a bit longer than R7, but it doesn't matter. But the matter here that actually this thing is reducible. It's new thing. It's not this R6. It's another invariant. It's new invariant. All right, and its weight is 21. Right, because it's 24, right? That's 3, that's 21. 21 was not listed here. And you can't obtain it from these numbers. It's new thing. So that shows that generators here is, if you'd like to do a polynomial, my next step is to add R6 prime. And that's not the end of the story. There will be new generators. And I actually don't know whether in polynomial terms, like in Hilbert's theorem, it's possible to do it in finite terms or not. So that's actually already in this classical story, which goes from Sophos-Lee, there's something that I don't know actually how to answer. So even though like clear what to do, we completely list all invariants, we can list all equations, right? Up to certain complexity, just like do finite list. Complexity will be order and degree, right? If I bound both, it's possible to effectively write everything. But yeah, so this theorem is tricky. Okay, so that's end of the essentially contact story for scalar case. Very similar story with essentially point. Those point transformations which are not fiber preserving. So very similar stories. There are 3 subcases, one smallest dimensional. Actually, if I'm going to write the formulas will be so similar, and because there's some relations, there's some drop of dimensions, there's some increase of order. I don't want to talk about it because basically, yeah, I showed to several people, like to Oliver, to Sokolov. I mean, they will not like persuaded it's really new. They didn't know, for example, this theorem or whatever. But I mean, the least you can extract from something. So that's from in our work that takes, I don't know, the first couple of pages. And then we actually go to systems. And I don't have time to talk about it. Yes, it's good, but it's much longer story. I mean, the invariants are not that awful. It's not wallpaper, right? Something which you compute in Maple and then just copy paste into TeX. But still, I don't want to talk about it in many details. I just indicate some particular things which happen in there. So here the alphabet was differential, well, like alphabet, but keywords were differential invariants, absolute differential invariants, scalar ones, right? Because we needed one function which defined a scalar ODE. Now we need to define pairs of ODE, so we need two functions, right? So we would like to write something like f equal to 0 and g equal to 0. Right, and there's Lie algebra G of vector fields. Now, of course, when we talk about systems, right, the number of unknowns is greater than 1, and by Lie background, we know there's no contact at all, it's just point, but still we discuss the same question. Like generically, the symmetries are fiber preserving, and we would like to list those which are not, essentially point. Okay, so that tells you that this algebra, so first of all, of course, if it's primitive, right, primitive means doesn't preserve any foliation, then it's already good algebra, right? Then it cannot be reduced to fiber. But it may be imprimitive, it may preserve some foliation, but still not descend to fiber preserving, right? Because what do we have now? Now we have this picture, right? Y1 up to, okay. I try to write up and down, write down is derivative, up is indices, right? So that's just J1, J0. Right, and fiber preserving are those which preserve this fibration. So let me just talk about m equal to 2, which is what's drawn here, right? So 3-dimensional space, and then fiber preserving is something which preserves 2-dimensional foliation. So in principle, also G which preserve just 1-dimensional foliation, but not 2-dimensional foliation will do. Okay, so what we do? We go to classification. There are classifications still in 3D of vector fields in 3D, and first extract all. So again, it's obviously of vector fields in 3D. Now not contact, it's just usual vector fields 3D, right? And then we look to primitive. There's some number of cases. And there's 3 algebras which are minimal, right? There's tree and there's inclusion tree. We just look to minimal because if classify invariance with respect to minimal, then classify list, then list invariance with respect to all. So this one are algebra of killing vectors. Vector fields indeed, but for Minkowski metric. So let me change here to this. It's just 2D.
Speaking about reducible.
Primitive means do not preserve any foliation at all.
With no invariant foliation.
Mm-hmm. Then I cannot, because now we talk about point, right? But they cannot be reduced to fiber preserving. That's the same for space form with non-zero curvature. Right, because a zero curvature, non-zero curvature. I'd walk over C, there's just 0, non-zero. Over R, of course, will be positive, negative, right? And then it's also SP4 here. It's not previous SP4, which appeared before. It's another SP4. It's primitive SP4. I mean, we talk not about abstractly algebras, right, but about represented as vector fields. And this, of course, differ, right? And in fact, in terms of this diagram, now cross will stay here. That's so that acts on P3. So previous act on compactification of Heisenberg, that acts on this. And then in primitive, that's minimal. There's three cases. They're completely different. And well, this P3 is what? This P3 SP4C, standard representation is four-dimensional space, standard symplectic representation, and you just projectivize it. That's how you get the section, right? Just projectivization of standard four-dimensional space where this is naturally represented. In primitive, with one-dimensional invariant foliation, but not two-dimensional, right? Because if two-dimensional, then it's fiber preserving. That's the majority as such. Okay, so who are those? That's SL2 semi-direct. That's old guy Heisenberg. But again, that's a different story. And then there's two SL3. That's different one. So we can write vector fields. They actually these are what? That's one-dimensional invariant foliations. So we can think as follows. So there's a Z here, and there's X and Y here. And that's one-dimensional foliation. We can always make it del Z. So these vector fields are lifts from two dimensions. Right, so they actually this represented in two dimensions, and they're lifted in 3D. And this differs follows. So if you look to vertical part, what happens with dz? So then one of them is preserves like symmetric structure, is just dz times factor which doesn't contain any z. So it's like just translation along z. So it preserves metric in here. While in the other vector fields here, which we look to dz components, there will be del z, z del z, and z squared del z. So it's actually projective story in here. So you see projective structure in here. So that's how these guys differ. Okay, so there are 6 things, and for 6 things we have to do something, but now the situation is a bit different, because when we, for example, do this, LXF, right, what will we get? Well, that's of course actually in big stratum we can always, if this is invariant equation, we can always choose both to be absolute invariants. But when we talk about singularity, situation changes. We need something analog of relative invariance. So you observe something like this. Okay, let's just do this. 1, 1, 1, 2, 2, 1, 2, 2. Right, and so what do we get? But this J infinity now is different J infinity because J0 now is this. No, of course. Yes, we can change it. Of course, there's just one change of generator. That's precisely the thing. So, for instance, if F and G have different orders, then the lowest invariant, of course, is just relative invariant, right? But if F and G have the same order, then in principle, neither of them have to be relative invariant. So what we talk about actually relative vector valued things, right? And then natural will be these matrices. Sorry, I wrote something wrong. That's something wrong. No, that shall be different thing here. So it shall be GL2 with values in polynomials on J infinity.
So what do you want? You want that does mean that this function should be a linear combination of everything.
No, if regular function, right, then actually it shall be, right? Because even in previous case, when right f equal to 0, we can change f to like f times some function, but this function has to be non-zero, right? That's usually defined like regular defining function. Of course, there can be some.
It means that they belong to this idea that it's completely different combination of everything.
Okay, so I agree if you talk about algebraic story. If you talk about analytic story, right, remember this one, then actually I can talk about regular defining functions. I can require that the differential will give basis in normal bundle. And then actually the change will be this. Yeah. So I can do arbitrary combinations, right? Because if I take product, I will get something that vanishes to higher order. That's not regular defining function. Mm-hmm. That's right. Well, so it's actually going to be difficult problem right away. So, but what happens here? So we actually go and study singularities as jet order grows, and we observe some like relative invariance and like this vector valued relative invariance, but there appear also so-called conditional invariance. They can be absolute or relative. Right, so what is this? So for example, if this has order k and this has order L and k greater than L, then this is a relative invariant. So if this whole system is invariant, then also G equal to 0 is invariant, right? Because it appears before as we go in prolongation order. But then F need not to be invariant in any sense. So what you can do, you can just take this equation, G equal to 0, restrict to it, prolongation, right? And then F will be actually invariant only mod this equation. And this is absolutely inevitable. There are some invariants that are just restrictions of invariants which are invariant in ambient space, but there are some which are conditional and cannot be obtained in this way.
It means that lambda should be a combination of.
Yeah, well, it would mean actually this triangular group, right?
No, I mean the lambda. It's not number. It's not partial function. It's just operator derivation, total derivation. That equalize your.
Well, it will be very difficult if you go this direction, I'm afraid. So let's not discuss it. But I mean, it just in terms of just scalar invariance, we can expect that this is generated like by two different like absolute or relative invariants if we can bring this by change of variables to diagonal form. And in general, it's not possible. Conditional, I think we can bring it to triangular form.
Well, but I wonder, will it all remain true if, well, let's take a degenerate example. F is a prolongation of G.
Mm-hmm.
So it is actually they are not independent in differential sense.
No. Of course, this we will consider as not as determined system. This we will consider as undetermined system. Yes, I did not say the requirements.
Should be added
Yeah. We of course assume it. So we take their symbols; they have to be independent.
You should add k equal a. So they have the same.
Yes, this is the best.
No. Then I will not list all equations because then I will not be able to list all equations. So my problem was to list all system of ODEs such that they have essential point symmetry algebras.
So, but if you take k equal a, then it
No, we treat both k equal to L and k not equal to L. It's just different problems. And sometimes conditional appear. And that's actually interesting story. So you restrict to g equal to 0 in this prolongation, right? And then you have to write one more equation there. And you just completely restrict to this, right? The group act there, and you look to differential invariant there. It's well-posed problem. Differential group acts on equation, and you compute differential invariance there.
Then your notion of invariant is not correct.
I didn't write any notion of invariance so far. I was writing analog of relative invariance, but I say that this is not enough. So we need other things. No. So that my notion of invariant is the following: that should be invariance of manifolds in jets. That's my notion of invariant.
Yeah, but in jets, if they have different order, you should take prolongation. So
I do this, of course.
then you should change it down.
Sorry, this was talking. Yes, that's for k equal to L. That's yeah. I confused story. Yeah. I confused story. But the general problem is different, right? But I mean, there's no this problem when k is not equal to L. It's different story. Yeah. I'm sorry about it. Yes, I confused. Yeah. This particular story is precisely for the same order. Okay. Yes. So then theorems here looks like, well, so of course there's absolute invariant general strata, and then there's some number of singularities, right? They're related to scalar relative invariance and appear also conditional relative invariance and things like this. So the answer is not long. I don't have time and space to present it here, but yeah, but that's majority of the paper. Okay, so I would like to show some peculiarities which we observed.
Can I ask one question?
Yeah.
What happens if m of the dimensional variable will be equal to?
No, we just consider two. We just consider two because we actually rely on classification, right? We actually rely on classification. It is possible to go beyond. It is possible to go beyond. We know how to do it. We wrote something about generalization at the conclusion of the paper because we don't need complete classification, right? So that's of course that's that point for complete classification. However, we can ask just about primitive. Oh, this are well. That's not big trouble, right? So primitive in 4D actually in any dimensions are done, right? But like for 4D, it was done by Poe in previous century. And then analog of those things, right? Will be lifts of things from 3D, which also exist, but the number of cases grows enormously, and branching grows. So even though it's clear how to do it algorithmically, already this took something like 20 pages. Yeah, so and a lot of computations. So I think it will be a very difficult problem, but formally doable. Now, what we needed here, right, in this thing, this was kind of important. We need, classification, better actually to say again, list. Because honestly, Sophosly did not bring it to normal form, didn't say that this differ from this, right? Like unique for parameterization. This was not done, but it's close to classification actually, not very far. And we observed some actually interesting phenomena there. So I have probably time for one phenomena. Let me just mention phenomena about this guy, SP4C, right? I didn't write how it looks like in vector fields, but then I will need to write 10 vector fields in 3 dimensions. But that's not very difficult, right? As I say, you take linear vector fields here and you projectivize and you get them in there. And actually they are written in here in affine chart. What we observe is that there is one relative invariant there, and it has this form. Я сейчас вытру, это уже не нужно. So right, so we have Lie algebra, fine dimensional, or we can say actually, well, fine dimensional Lie algebra acting on J0, right? And then we lift it to there. It's kind of very intuitive to assume that the following will happen: that after some prolongation, there's stabilization, there's like isotropy of generic point is 0, right? And there's free action, right? So kind of very natural thing. And Sophus Lie just assumed it everywhere, but actually Sophus Lie never proved it. So he was, that's just for fine dimensional Lie groups, right? To do prolongation, of course, well, this becomes big. Well, I don't know, let's put here K, right? This becomes big. This is the same. Abstractly, they are isomorphic, right? But of course, represented differently. But then it's become free action on open structure, right? That actually was proven only recently in generality by. So let me say precisely. Was a paper by Adams-Olver, 2018 in Transformation Group. So-called prolonged analytic connected group actions are generally free. That's precisely what the statements they proved. So they on in complement to Meagher said, they say it's just free action. It's certain analytic work there, right? One might think about the following situation. So what if we actually take here some equation, right? And do the same store equation, which is invariant, and do prolongations. Is it actually true? And the answer is actually, well, of course. Of course, in general, not true. For example, consider the motion group in S3. 3 rotations plus 3 translations. Consider its action on lines. The space of lines is 5-dimensional. The group is 6-dimensional. It can't act freely there. That's invariant sub-equation. Space of lines, right? Double derivatives equal to 0. Right? So you have x and y and z, and you write y2 equal to 0, z2 equal to 0. Well, you know, space of lines, right? And that's group, of course, pretty of lines. But the group 6-dimensional equations, 5 dimensions, finite type, whatever you prolong it, it's the same, right? So the group cannot act free. But is it possible that equations infinite type at the same thing happens? And yes, and that's what we observed. So we had this equation y2 z3 equal to z2 y3. So what are these? These are equations for curves lying in a plane, right? So, and
equation to what?
Well, it's actually equation for curves that belongs to one plane.
Plane.
Yes, and SP4 preserves this, but it never resolves. So you go to jets of those curves, and no, no, that will be underdetermined. Yeah, that will be underdetermined. So it's actually infinite dimensional when you prolong it, right? There's enough dimensional space for group to resolve, for algebra to resolve, right? So algebra is 10-dimensional. This is infinite dimensional. It never resolves. There's always stabilizer.
And what's that stabilizer?
Well, the stabilizer is the following. So this SP4 has the following graded structure. That's SP4, right? And this is 1-dimensional. This is 2-dimensional. That's 1-dimensional. That's 2-dimensional. That's what 4-dimensional, right? So the root diagram is this. So there's 8 of those things, and there's everything on 2-dimensional Cartan Cartan algebra, so plus 2 more dimensional, altogether 7. So this thing is G0, that's GL2. This thing is G minus 1, this thing is G plus 1, this is G minus 2 plus 2. So this thing actually X trivial on this 3-dimensional story. No, yeah. So so it never resolves. There's one generator that actually always sits in the kernel. It's not in the kernel. It's actually, it depends on jet. So that's effective action, but for every point there will be isotropy.
So you found vector field that field is really zero of this equation at all.
It will be changing. It will be changing from point to point. It's not the same vector field. Otherwise, it just sits in the kernel of the action, right? But then it will be actually ideal, but there's no ideal in SP4. It's simple, right? No, it changes from point to point. It's effective action, but for every point there is isotropy. That's kind of a funny thing. I don't know. So I mean, just studying those all algebras which appear in here, it's just kind of from event and my viewpoint contribute something to this theory of invariance.
It's only phenomena for undetermined.
Well, I wanted this to be infinite dimensional. If I talk about determined system, it will be finite dimensional, right? Well, just all derivatives are expressed, and prolongation will be isomorphism. So yeah. So maybe I can also do finite dimension, but that's not interesting because for finite actually it's more predictable.
Yeah, but we're talking about ODEs.
No, we observed it, of course, from this case when G was precisely this, and we were looking for F. We observed it precisely studying this problem. G was third order. We were looking for K of higher order, which is invariant, and then we observed that actually it's never completely resolved. It's not a problem at all for the theory of differential invariance, but it's actually a problem for the method of moving frames, but Felsenhofer, for example, because they always need free action of the groups. And so that's like theorem by Adams and Olver was important for them because when they can do free actions, they can construct moving frame. There's no free action. Moving frame doesn't exist. Okay, thank you very much.
Okay, thank you for a very interesting talk. Questions, remarks?
I have one very strange question because you talked the word primitive, which 30 years ago I heard and I never did. It was a theorem I remember about group of analytical symplectic that if the group is primitive, then can you share some comment, give me some comment about
Maybe you talk about Kobayashi-Nagana theorem, then actually either it's infinite, right? Or it is has at most one non-trivial prolongation.
Okay, for example, primitive, imprimitive, you tell definition. If you consider group of symplectic transformations of group, it is primitive or imprimitive?
Symplectic, fine dimensional, infinite dimensional. Well, if we talk about this one, right? Then it is primitive. But yeah. So like it depends on how we represent it by vector fields.
Depends on presentation.
Yes, depends on presentation of vector fields. I can always multiply space by one more dimension in which the action will be trivial. Yeah.
It's not a property of an algebra, but of its representation in vector fields.
Yes.
So
yeah, but like there's the smallest dimensional representation by vector fields of this algebra is 3, and there are and there's precisely 2 different primitive actions. Right? One is reduced. One is actually reducible, the other is irreducible.
More questions? Женя, you traditionally ask questions.
Okay. So thank you very much.
Да.
Есть связь между Лоренсом, вот там, Ментовским,
Да.
и вот этими SP4?
Конечно, это же конформно.